Hello everyone. So today we're going to be looking at using formulas to find area. Now this is something that your students should have a good grasp of, at least regarding rectangles, triangles and parallelograms, by the time they finish year 7. Now this is something that they're going to keep building on as they move into years 8 and 9. They'll be using areas to solve problems. They'll be using areas, looking at compound areas, and they'll actually also be building on it as they look at volume, building volumes out of faces. Ideally, your students should already, by the time they reach year 7, have come across a reasonable amount of concepts regarding area. This begins by about year 4, when we start talking about informal units to measure areas. So informal units might be using something like, take a shape, cover it in beans or paper clips or some other thing to count how much of a thing you can fit on it. By year 5, hopefully they've moved on a bit and they have this idea that maybe beans are a terrible thing for measuring area with. Squares, regular shapes, that's what you want to go for. So they should be using standard units to measure area by year 5. By year 6, they should be expanding on this. They should be being able to apply the concept of area. Hopefully they're also talking about the area of a rectangle, length by width. Maybe they've encountered some formulas for other shapes too. We'll see. Even so, a lot of students really struggle with the concept of area. So one area that students really struggle with is making the jump from the counting method of area to the multiplication concept. And this is something we see even students who happily apply it to like the area of a rectangle. When it comes to, say, finding the area of a parallelogram here, they're okay at the start with the square in the middle, but then when it comes to adding on each of these, they're just adding them all on individually. However, even if your student, when asked what's area, if they say length times width, doesn't necessarily mean that they're properly differentiating between the concept of area itself and just the method for finding area. And this can make them struggle possibly when they encounter new formulas, new concepts related to area, if they don't understand what these formulas are actually trying to tell them. A really common problem with students is getting mixed up with their formulas. So the most common one you might see, if students have been given formulas in the past for measuring perimeter, measuring area, they get them mixed up. Or they can't remember which formula applies to which shape. The main reason for this is probably just, by this stage, they may well have seen just tons of different formulas for area, and it's just remembering which ones go where is a real struggle. But it's also due to them not understanding what these formulas are telling them. And so they don't understand. If they don't understand how multiplication is related to area, they're not going to see that addition in a perimeter formula isn't going to be telling them an area. If they don't understand where it comes from, they're not going to understand how they relate to each other. A similar problem is maybe understanding the formula or knowing what the formula is for a shape, but getting confused between measuring the sides and measuring the base and the height. The reason for this is probably largely because the first shapes that they encounter formulas for are squares and rectangles. In the case of squares and rectangles, the side lengths are the base and the height. And if they don't quite get the right concept, when it comes to new shapes, they don't know how to apply it. So I've got a quick activity today to hopefully address some of those issues, some of those misconceptions. Ideally, your students are coming into this with already understanding the area for a rectangle fairly well. Hopefully some of your class will also be comfortable with the formula for a triangle. If they're not all quite across the idea of multiplication, if some of them still prefer to counting, probably going to be okay, as long as some of the students in the class, a decent number of the students, are comfortable with some of those concepts. The idea here is we're going to get them hands-on, and we're going to get them talking to each other about these concepts. So what you're going to start with, come to class with a whole stack of parallelograms that either you've cut out, maybe if you've got access to a guillotine, it might be too hard, or just print them out, get the students to cut them out themselves. Should be okay, get them hands-on right from the start. Now, we want to get a good variety to get the discussion going. So just for a start, have the students work on their own. Hand out the parallelograms, ask them, can you find the area for me? Tell me what the area is. Some of the students will be all over that. They've already seen the area for a parallelogram. They just, bam, base times height, done. Maybe you can ask those students, see if you can come up with a new way. See if you can come up with a way to explain the method to someone. Other students, they might really be struggling. They don't even know where to start. To get them going, you might want to bring in a variety of tools. If you bring in some grids printed out, or maybe on a transparency, they can play around with that. Some pens or things, get them string or whatever you can think of. Maybe some informal units or something to get them started. Then, give them 5 minutes or so. Hopefully the students that are struggling, they're still in that area of productive struggle. If they haven't got an answer yet, they at least have something they can discuss to their friends about. Don't leave it too long. Some of the students will get disengaged. It's not a terribly onerous problem if you know what you're doing. So at this point, pair the students up or get them into groups of 3. Have them discuss their solutions. Did they get the same answer? Did they use the same method? And you want to focus on the method. Maybe they did use different methods, but they got the same answer. That's great. That gives them something to talk about. Now, once they've got a few ideas on the plate, this is when we bring out the scissors. So you're going to tell the students, okay, we're going to use a method here, and some of the students hopefully have already hit upon this idea. We're going to take our parallelogram and we're going to chop it up, and we're going to turn it into shapes that we already recognize. So there's tons of ways students might do this. A few that come to mind: you could take your parallelogram, chop it across diagonally 2 triangles, or chop it into 2 triangles and a rectangle. Maybe some of them might have seen it before and might come up with it on their own, of the standard method, turning your parallelogram into a rectangle. But some of them might just want to chop the parallelogram up into confetti and count how many pieces they get, and maybe that's okay. As a group, hopefully they'll be able to settle on something that they're happy with, because at this point, give them maybe 10 minutes or something. It shouldn't be too long to work out how to chop something up, have a bit of a discussion. Once they're happy, you're going to tell them to bring in their solution up to discuss in front of the class. Now, the advantage of this is they've got a physical model. They don't have to explain to students, oh, I'm imagining this is this. They can show, I chopped it up, I've got 2 triangles, I've pushed this, and now it's here. You might want to record these on the board. So make a list of what everyone's tried, and that's going to facilitate some discussion. What do you notice is similar about these? What's different? Are any of them equivalent? What happens if you turn it on its side? What happens if you, will the method still work in different circumstances? There's a whole lot of stuff you could talk about here. You could even, if they're comfortable with formulas, get them to put up, work out if they can write up a formula for each of these. And that's going to prompt things like, well, which of these is going to be the easiest to calculate? Things like that. Hopefully, they start to settle on an idea. Maybe, as you put these all up on the board, some of them have, maybe they've chopped across the opposite diagonal. Maybe some of them have their parallelogram on the side. And that leads into all sorts of discussions about, well, hopefully, this is the same shape, right? Using a different base and a different height, but it should give you the same area. I think it's important at this point. Hopefully everyone's got a bit of a grasp. You can have a chat about what the students have learnt. Make sure they reflect on it. Make sure they've taken something away. They've seen a few different methods and they understand how those methods actually relate to the concept of area. It's not all just about memorizing formulas. To consolidate it, maybe you get them to have a bit of a, do a few problems. Hey, can you find some parallelograms? I think at this point, a fun option would be to just whip out a whole stack of new parallelograms. All the students who haven't tried one of the successful methods, they can have a go, see if they can get the same answer as everyone else on round 2. Okay, so hopefully this will give you something to think about. And yeah, don't forget to like and subscribe.